In the past, we've seen the connection between integrals and areas. So you could think of the integral as the area under a curve. So when we have this curve, the integral gives us the area under it, which is equivalent to giving ourselves an infinite sum of infinitely thin rectangles that come up to that curve. But if we can do it with areas, is there any reason we can't take this one step further and start doing volumes? Some volumes are fairly easy to calculate. Understanding the definition of volumes makes it easy to calculate the volume of a cube or any rectangular prism. You take length times width times height. We can extend that to any shape that has parallel sides. The volume of a cylinder is easy to imagine as the area of the base, or pi r squared, multiplied by that third dimension, height. But what about some other volumes that we've seen? Why is it that if you take that same cylinder, instead of having parallel sides, you have the sides taper to a point and make a right cylindrical cone? Well, how do we get that the volume is 1/3 pi r squared h? How is it that we can take a sphere which has no straight lines, no right angles, it's completely uniform, this 3D shape, and determine exactly that the volume is 4/3 pi r cubed? Is there a way to do this? Well, the answer, not surprisingly, is yes. And the basic concept is as follows. If you can come up with a cross-sectional area for your shape at different points, well, then you could take the infinite sum of these areas multiplied by their widths, and this should give you the volume. So in the case of our sphere, we're actually adding up infinitely many cylinders that make up the sphere. So we've taken our sphere and we've sliced it into thin wedges. So just like we approximated the area under a curve with rectangles, we're going to approximate the volume of a sphere with the volume of the cylinders that we've made it from. So this is what we're going to be calling volumes of revolution. And we're going to be doing this by taking the curve that describes one side and revolving it around the x-axis. And that revolution is going to give us our 3D shape. So we can take that one curve, revolve it around, and make our 3D volume. That is the basic concept. And in the next part of the video, we will look at the integral that does it in general, and then apply that integral to find the volumes of spheres and right cylindrical cones. So we can then use this concept and extend it into the volumes of arbitrary shapes.